Okay, so after Wednesday's class, I went home and I was just like, man, I don't know if I can. I don't know if I could teach the entire course the way Professor Zhu teaches this course. Now, I have the highest respect for Professor Zhu, and his notes are very good, but I think I would have a hard time teaching the course based off his notes, and there's just no way I can make the class the way he makes the class. So I had like this identity crisis on Wednesday. I was like, oh man, I don't know how I'm gonna get through class. So I think I'm just gonna take the course a little bit different from what Professor Zhu had laid out. I'm a little bit more comfortable if we have a textbook that we can kind of work with. So at least for the first half or so of the course, I think I want to work out of this textbook, Applied Multivariate Statistics with R. It's available free on SpringerLink. Okay, so you can just I'm just using the digital copy. So you guys just use the digital copy. It's really easy to get. As long as you're on the UCLA campus, you can go, just go to Google, type in SpringerLink, okay? You go to SpringerLink, it looks like this. If you're connected to the UCLA network, whether that's because you're on campus or you're connected via the VPN. If you live off campus, you should all have the VPN. You got a UCLA address, get your VPN set up, okay? You can even get it like set up on your iPad, and you can go on, get all these network journals or research journals and stuff. And then so just type in multivariate statistics R, and in your first text there will be Applied Multivariate Statistics with R. You can just download the PDF, or you can download chapter by chapter, so you don't, so it's, I guess, easier to navigate if you want to do it that way. And I think I'm just a little bit more comfortable doing a bit more of a practical approach within R and things like that. We'll make reference to kind of some of these equations and theoretical stuff every now and then, but I think I'll be a little bit more comfortable in the teaching the class this way. I hope that's okay with you guys. Just because I was like, oh my gosh, I was just felt like I was having a panic attack after Wednesday's class. So that said, I didn't have time to prepare a full, I guess like a full lesson and whatnot. So I think I'll just try to show some matrix operations, some stuff with vectors and matrices today in R. I know some of you guys are already very familiar with the matrix tools that exist in R. But for those of you who are not, maybe today we'll be able to serve as kind of a quick refresher or just overview of some of the stuff we can do in R. And then by next week I'll try to have kind of a data set that we can work with and show you how these matrix operations are applicable to a quote real life data set. It'll probably not too complicated, just so we can illustrate the exact things that we're doing. And then and we'll go from there. So, you know, if I were to have taught off of Professor Zhu's notes and stuff, you know, he had homework assignments lined up and everything, and so I think I'm going to have to try to rethink homework assignments and exams and whatnot. So please just be patient with me as I'm kind of wading through this novel course content myself. And so the multivariate statistics, this will cover, you know, principal component analysis, factor analysis, a lot of these matrix and vector operations, eigenvalue, this type of stuff. And then as for, you know, what do we do with the other portion of the course? I'll have to figure out that stuff when we get there. So, so anyway, we'll get started. I think, you know, one thing that would also be of interest would be kind of displaying multivariate statistics or just some kind of graphical displays, which, you know, we don't have a designated course on graphics in R, and so maybe I'll throw some of that in there. But okay, well, we'll see what we can do. All right. Okay, so maybe I just have to back up a little bit. Anyone here not that familiar with R? So okay, all right. So there are a few of you. Okay. Well, okay. So if you're not that familiar with R, that's okay. So what you'll want to do is go home, go to Google, just type in R, and your first hit should be R project for statistical computing. So you're going to go there, and you're going to go under download CRAN, and then probably download from the UCLA mirror. Okay, or you can just type this address in directly, cran.stat.ucla.edu. You're going to download the appropriate file and install that. And then once you have R installed, I like to install R Studio on top of that. Okay, I guess just click download R Studio Desktop. Okay, and just get the free one. All right, you don't pay $1,000 a year. I mean, unless you have $1,000 to spend on tech support, but get the free R Studio and install that. So you have to install R first, and then you install R Studio. You start it up, and it will look something like this. If you have zero familiarity with R, I highly recommend just checking out some intro books. So if you're on the UCLA campus, go to proquest.safaribooksonline. Okay, proquest.safaribooksonline, and then just type in R. Whoops, not R3. Okay, and well, there's all sorts of stuff, but getting started with R is kind of this is just a very basic book that will get you started. Okay, if you've used R before, this book will be useless to you. But if you've never used R, this might be a good spot to begin. All right, so let's talk about matrices and vectors. Okay, and so I think a lot of you guys are already familiar with vectors, but we could create a vector A using the concatenate function. And so I can just do like 1, 2, 4, 6, 8. All right, and so here A is a vector. And I know, kind of, we can, on paper, we can treat vectors as kind of these, matrices with, column matrix or a row matrix. But R does not treat it as such. If I ask for the dimensions of A, it will say there are no dimensions. But I can assign dimensions to A and say, I want it to be 5 rows and 1 column. And then so now when I ask for the dimensions of A, it says it's 5 rows and 1 column. Okay, so the dimensions is always rows first and then columns next. And then when I ask for A, it reports it as a matrix with 1 column. Okay. So you can ask A the transpose of A. Just asking, put T of A that way. Okay. And so we can get do the dot product of A. So let me just take B, duplicate. B is just a copy of A, but I'm going to get rid of the dimensions on B. Okay, so the dimensions of B we will set null. Okay, so B is now just a vector. A is a column vector or single column matrix. B is a dimension. And so if you do things like B star B, this will do element-wise multiplication, and you can see it's multiplying 1 by 1, 2 by 2, 4 by 4, 6 by 6, and 8 by 8. And so the dot product would be the sum of B times B there. Okay, so that would be our dot product. Or if we treat it as the column vector, we can do kind of the you have matrix multiplication, which is this percent star percent. Oh, so I have to transform. Oops, I've done it the opposite way. And we will get the same result that way. Okay, and so this actually brings up an interesting point. If we recall matrix multiplication, okay, the let's just compare the results that we get here and here. Okay. Over here, A is 5 by 1 times 1 by 5. Okay, and so the result will be a 5 by 5 matrix, right? And then over here, it's just the opposite. It's 1 by 5 times 5 by 1. And so this results in a 1 by 1 matrix, okay? And so, you know, as you are doing matrix multiplication in R, a lot of times, you know, especially if you're writing a function or you know, writing a loop or things like that, it's good to test out your matrix multiplication operations outside of it, and just make sure you're going to get the results that you're expecting, because I know it's just very easy to kind of get things mixed up. You're going to get you know, decidedly different results, and without kind of that element to check your own work along the way, you can definitely confuse yourself or make major mistakes there. Okay. Let's see. So we have kind of this cross product matrix multiplication, which is the percent star percent. This is kind of your standard matrix multiplication that you've probably learned in your, you know, basic linear algebra class. We can make larger matrices. So let's say I'm going to create matrix D, and we'll just say matrix D is going to be the elements 1 through 16. The number of rows is 4. Okay, and when you ask R to create a matrix, it fills in the elements 1 through 16. It fills them column-wise. Okay, and that's just how it works. If that's not the way you want it, you can ask by row equals true. Okay, and it will fill it out row-wise. Okay, but we'll stick to our column-wise matrix, and then maybe I will say F, on the other hand, is going to be another matrix, maybe 11 through 22, with the number of rows equal to 3. Okay, so F is a 3 by 4 matrix. All right, and so now I can multiply F by D. Okay, and so will this work, or will this give me an error if I do F times D? So D is 4 by 4 and F is 3 by 4. Okay, that one works, right? Okay, because it's the inner dimensions have to line up. So we have, you know, F is 3 by 4, basically percent times 4 by 4, and so the inner dimensions line up, so we're okay. All right. If on the other hand I did D times F, it will say non-conformable arguments. Okay, and that's because I've got a 4 by 4 times a 3 by 4, and so the inner dimensions don't line up, and so it errors out. Okay, and so, you know, if you're doing if you've got something like this and you get something like non-conformable arguments, there's a good chance that you've made some kind of silly mistake, like so. Okay, so we have this this operator. Okay, we also have the outer product operator. Okay, so we have outer multiplication, and so we can use this for we can take a vector. So so B is 1, 2, 4, 6, 8, and I can do B star O star, or I'm sorry, percent O percent, and this will be outer multiplication, and basically it's taking 1, 2, 4, 6, 8, and 1, 2, 4, 6, 8, and it's kind of, it puts those on the margins, and then it multiplies everything together, and the resulting values appear, fill out the entire matrix. So this would be the outer products. Okay, so these are just some matrix multiplication tools that we have there. We talked about norms, and there isn't like a built-in norm function in R, okay? But we can talk about like the Euclidean norm, or whatever it might be. Okay, so let's one way to think of the Euclidean norm is that we can think of it as the distance from the origin to the coordinates of a vector, okay? And so, you know, if you've got just if your coordinate is for x is 3 and 4, what would our Euclidean norm be? Um, 5, right? Because a 3, 4, 5, you know, yes, okay. All right, so, you know, how can we write a function that will calculate the norm? So I'm going to, I guess part of me is assuming you guys know how to write functions and stuff. Like, I know those of you who are in my 102A class definitely should be able to write a function. And so, because if I said write a function to calculate the Euclidean norm of a vector, can we do that? Yes? Okay. All right, so let's write a function to calculate the Euclidean norm. All right, so we'll just write. Oh, there is a norm. What is? I don't know. It calculates a matrix norm of X using LAPEC. Well, all right. Well, I'm not sure what that is actually. I say there's no function for norm, and then well, let's just see what norm of X is. And if it's 5, yeah, no, it doesn't. It doesn't like it. Okay. So so we're gonna make it. We'll make a new function, and we'll just call it E norm. All right. And so this is gonna be a function where we take some vector x, okay, and what would we do? We would square each element of x, right? And then we would add them up, and then we would take the square root of that, right? And that should do it. Okay, so I mean, this is just basically give me like you've got two sides of a right triangle. You're going to square side A, square side B, and you add those together, and you get c squared, and you're going to take the square root of that. Okay, so this should work. All right, so we got x is 3, 4. What is E norm of x? Oh, good, it works. Okay, 5, and then so you know we could try. Let's say, and this should continue working even if I have a a 4-dimensional vector. we can get, this would be the norm for, I don't know, the Euclidean norm for this four-dimensional thing, okay? Now, if we didn't want the Euclidean norm, let's say we wanted the Manhattan norm, okay? Or the L1 norm. So the L1 norm, what is the L1 norm? So we'll call this M norm. What are we doing there? Basically, we're not squaring them. We're adding things up together. Okay. So we're going to just say the sum of the absolute value of x. Okay, and that's simple enough. And then if we wanted anything else, we could also just the L3 norm or the L infinity norm. Now this the L infinity norm, R would get angry at us if we asked it to try to do the L infinity norm, just because the way it handles infinity is not mathematically, I guess, sound. It just says, the way it stores infinity is actually, it stores it as just kind of this number that just says it's bigger than the biggest number I can think of. So, and it calls that infinity. So the infinity norm would actually just be the largest element in our vector. But well, we actually don't have to get into that. Okay, but so we can write functions to calculate norms for us, and these can be useful if we wanted to deal with norms, or so we have that. We can also we can calculate determinants, okay? And I didn't go over the notes for determinants from Professor Zhu's notes, but the determinant, well, I don't know if anyone wants to try to explain what a determinant is, but basically you're just taking some matrix, okay, and then you create all of these minors and whatnot, but you're taking a matrix and you are giving it you're basically boiling it down to a single value, okay? And so a matrix, well, it's got to be a square matrix, okay? So you can have like a 2 by 2 matrix or a 4 by 4 matrix or whatever size matrix we've got, and you're taking those elements and you're boiling it down to a single number, and these numbers are useful, for calculating inverses of a matrix, or I don't know, just other operations. If you've got a 2 by 2 matrix, kind of a geometric interpretation is that, if your matrix looks like this, you've got a 2 by 2 matrix, you can think of these, the 4 spots of your matrix as the coordinates of a parallelogram, okay? Where one spot is the origin. You've got a vector out at point AB, a vector out at point CD, and then the resulting parallelogram will have an area, equal to the determinant of that matrix, okay? Or I should say the absolute value of the determinant of the matrix, just because you could have a negative thing. And so that's, that's one interpretation. And if you have a 3 by 3 matrix, it just kind of generalizes into a parallelepiped, kind of this three-dimensional prism, and it would be the value of the determinant would be equal to the volume of this corresponding shape, and it generalizes beyond 3 dimensions to however many dimensions that you have. Although we have a hard time picturing what exactly the volume is in those respects. Okay. But R has some just built-in functions here, and so if I just say H is a matrix 1 through 9, with the number of rows equal to 3, we can ask for the determinant of H. Well, it says it's 0 here, but I think that's because I just did it. Let me just let me ask R norm 9 plus 3. Okay. Okay, so we'll ask for the determinant of H here. Okay, and so now, it calculates these things quite rapidly. We have formulas to calculate determinants by hand, but why bother when the computer can do it just much faster than you may want to. We have there's all sorts of stuff, and I guess I have to maybe I'll give you guys some reading. In the textbook for applied multivariate statistics with R, make sure you read the chapter on basic linear algebra, and I'll probably assign from that chapter a few problems to work through. Okay, and so within this chapter, we've got the determinant, we've got these matrix operations. When we apply some matrix calculations and things, sometimes it's useful for the computer to calculate, say, eigenvalues or eigenvalue decompositions. Okay, and so you can think of eigenvalues as these how do we think of eigenvalues? If we were to multiply a matrix, okay, so let's say we've got a 3 by 3 matrix, okay, so we have a 3 by 3 matrix. We can multiply it by a vector, okay, and I can multiply it by a 3 by 1 vector, or 3 by 1 matrix. What is the resulting? What will be the result of this operation be? What will its dimensions be? It'll be a 3 by 1 vector, right? This vector that I'm multiplying by, this can be thought of as the eigenvector, and meanwhile I can take the another eigenvector and multiply it by an eigenvalue, And the resulting vector that we get, if I do a 3×1 eigenvector times its corresponding eigenvalue, will also result, the eigenvalue being a scalar, okay? This will result in a 3×1 vector as well, okay? And the key here is that the resulting 3×1 vector that we get from doing the eigenvector times the eigenvalue is identical to the resulting vector that we get by multiplying the entire matrix by the eigenvector, okay? You know, and so, you know, maybe I can demonstrate this. So you know, here I've got this 3×3 matrix H, okay? And I can just say, what is the eigenvalue? It doesn't like this because something's going on. I'm getting complex numbers, which we don't want. Let me just add some numbers to H. Am I doing something silly here? All right, give me a second. Sorry. Okay, so I think this is better. Okay, so I've got, you know, a 3×3 matrix H, okay, and if I were to just multiply this matrix by, you know, one of these vectors here, okay, so I can, I'll just call this, so I'll take the vectors and just the first column. Okay, so I'm going to take my matrix H and multiply it by this this column vector here, okay, and I get this resulting 3×1 vector, okay, and so keep an eye there. If I also multiply just our vector just by this single value here, okay, so if I do the eigenvalue of H values, take the first one and I multiply it by our column vector G. Maybe I'll transpose it here. We see we indeed get the same resulting 3×1 vector here. Okay. I don't know if I did this wrong. No, it's the same. And so we have, you know, R can do these eigenvalue decompositions very quickly for us, and I guess next week when we start looking at some data, we can see kind of how eigenvalues are useful in from a practical perspective, and a lot of times, you know, we can take these huge matrices, you know, like a 1,000 by 1,000 matrix, and run these quick eigenvalue decompositions to kind of essentially capture parts of that information in this strange reductionist sort of way. Okay, as we go forward in multivariate statistics, a lot of the themes that we'll see will go from taking high dimensional data, having like 30 variables or even 5 variables, and seeing, can we boil down multiple variables just into 1 or 2 useful variables. Okay, so is there a way to capture the essential variation that exists within a set of data into just 1 or 2 pieces of information? So for example, and I think we're already familiar with a lot of this type of stuff. So for example, you probably had to take the SAT exam to come to college, and what the SAT is trying to do is it's trying to take this complicated measure, complicated thing called intelligence, or maybe test-taking ability, if we don't want to get into intelligence, but just this complicated thing which is multifaceted, right? How good are you at all of these different things, and it's just trying to boil it down to maybe 2 numbers or 3 numbers. This is your ability for quantitative reasoning, this is your ability for verbal reasoning, and this is your writing skills or something like that. And it's trying to boil down your academic performance potential into just maybe 2 or 3 numbers, and that's supposed to kind of give the university an idea of how good of a student you might be, and that might even further be reduced down to 1 number, which is just your composite score, which you just add all 3 of those numbers up together, or add those 2 numbers up together, and this is incredible dimension reduction, right? Because if we just think about what are the different, how a student can excel in different things, you could have someone who's very good at, I don't know, this type of thinking, but not so much another thing. We can debate and discuss how we're supposed to measure someone's intelligence or ability, ETS and these standardized testing companies are, they're kind of trying to argue, it's only 2 dimensions or 3 dimensions that really matter, and whether that's true or not, they've certainly done a good job of convincing universities this is how this is a reasonable way to measure student performance, and this kind of theme of dimension reduction is well, that's the central tenet behind principal component analysis. You've got lots of variables, and you're picking out essentially the 1 or 2 dimensions, which we call principal components, as the things that we're going to try to measure and say this is the important feature that we see in our data here. Okay, so I guess we'll end there for today, and so start next week. I'll try to have a homework assignment produced, and we'll see how we're doing. Yes, question. I'm sorry. Yeah, so I'm gonna have to think of assignments for you guys, and we'll figure it out. So be patient with me, please.